vehicles are getting more energy dense, and therefore it's very important for us to start looking at the thermals of these batteries. We need to consider the thermal efficiency of a battery, because without understanding it, without optimizing it, we are unable to maintain peak efficiency, we're unable to maintain safety, and also get the longevity out of the battery packs. So how can we use simulation and SimScale to actually understand the thermals of these battery packs? How can we use them to optimize the thermal efficiency? And how can we actually create and design better cooling systems for them? Well, we can do that with our conjugate heat transfer simulation. We can do that by understanding a few main goals. So the main goals in our sense are going to be minimize the temperature of the cooling plate, thus wicking away the most amount of energy from those battery packs as possible. Maximizing the uniformity of those cooling plates. We don't want some batteries to be at higher temperatures than others and operating at different efficiencies. Also, we want to optimize the cooling efficiency. By that, we mean we don't want to have a pump that's as big as the car just to pump the coolant through the channels. We need to also make it easy to cool as well. Now, we can really make use of the scalability of SimScale with a few different ways. Firstly, we can help designers understand what their designs are actually doing using large parametric sweeps. They can do entire design space explorations and really get quick feedback as to what could be a good direction of focus for them when it comes to designing these battery cooling plates. Now, they can do this truly scalably. They can either do it in parallel, they can do this sequentially, but very quickly they're going to be able to build up a good, clear picture as to how these different designs, these different design factors can influence these main objectives. And we can also use AI to predict these designs. So we can actually run these hundreds of studies. We can train a model, and then we can get even faster feedback in a matter of seconds as to how these might actually perform, which is invaluable to a designer trying to get the best solution for his situation. Okay, so with that in mind, let's talk about SimScale. SimScale is, of course, a cloud-native simulation platform. So you don't have to have anything locally installed. You don't have to have any amounts of compute power just to be able to solve our simulations. It's all done within the cloud environment. And to start that process, the first thing that we do is navigate to the SimScale website. So we can go to the simscale.com website. You can see here our homepage. There's many useful resources here. But what we're going to do now is go to the top right-hand side and navigate to our dashboard. So the dashboard is what we call this space here. So it's a collection of all of our projects. It is where we do most of our administrative activities, including adding users to companies, managing projects, putting projects into different spaces, understanding our remaining resources, as alongside as any of our actual account management side of things as well. So changing passwords, API keys, all those things are done here. Now, once you've created a project, once you've picked a project that you want to work on today, we can double click on it, open it up, and that will take us into what we call the workbench. So if we double click here, you'll notice we load into a new screen, and this is what we call the workbench. So if I quickly load up some results just to put something visual on the screen here. The workbench generally consists of this large viewer space in the middle. So this large viewer space in the middle is where we can visualize results. We can graphically assign things to our setup, all within this space, and also inspect the geometries that we've actually uploaded to the SimScale platform. On the left-hand side, this is what we call the simulation tree. So the simulation tree is where we do all of our technical bits. So we define what environmental conditions our batteries are going to be in. We define what the flow rate of the coolant is going to be. We define what the power of the battery is going to be in this case. All of these things are done technically on the left-hand side. Now on the right-hand side, we have the support functionality. A lot of people really appreciate the SimScale support. You will see that on many of our reviews. And this is actually because it is live, it is real time. You can start a real conversation with our customer success team, who are pictured on the top right here. And this allows them and you to quickly come to an understanding and find the best way forward for you. Optionally, you can also share that project with us. It allows us to actually come in and see your project and tailor our advice based upon what we are seeing and how we are talking to you. We've also got many other administrative features, such as sharing amongst yourselves, your company, with all sorts of different levels of access. But let's talk specifically about this case now. So this is a battery cooling plate. I showed it in the presentation. What we've got here is a cooling channel that goes straight in, coolant in here, coolant out here. And we can see that it cools down this aluminium plate, and there is a power load that's been applied to this that heats this up. And it shows us how well we are actually performing here. Now, the first thing to note is that this is the post-processing area. So we'll have all of our different tools. These are the things that you can use to understand your design, the things you can use to help you get to the next iteration in your design process. Now, the first thing that I like to start with in this particular case is actually doing a statistics analysis. So the statistics analysis will give you a maximum, it will give you a minimum temperature on the surfaces that we've selected. It'll also give you the average. And you remember back to the goals that we defined in the presentation, we said we want to minimize the temperature, so we can use the average temperature as our function for that target. But we also want to get the best uniformity that we can out of this design. And you can actually see that there is quite a lot of variation. So some 8 degrees of variation here in terms of temperature. We would want to be optimizing that. We'd want to be iterating our cooling channel design to make sure that we get better uniformity. Also, we can get pressure drops from these result controls. We can use inspection points. We can use different fields to actually understand what those pressures are going to be. We can also do this as an output as a CSV file as well. And that will be our third and final goal. How fluid dynamically efficient is this system? How big a pump do we actually need to have to be able to get the coolant through the entire system? That's what we're being told here. And we can understand what those pressure differences are and make a decision based upon that. So that's the post-processing side. There are 3 targets that we're going to be obtaining from this simulation. Let's talk very quickly about how we as designers would actually go through the setup process and quickly realize design decisions, quickly realize what influence we have made in improving, or perhaps the opposite, of our design. Good. So that journey starts on the left-hand side in this simulation tree. We come to the SimScale platform, we drop a geometry, press a little plus button, drag and drop it into this space. We support most major CAD file formats, and once it's uploaded to the SimScale platform, we'll be able to inspect it. We'll be able to inspect that geometry in the viewer. Now we can do a few different things. We can make it transparent. We can also open it in a CAD mode to improve the geometry and make sure that it is simulation ready, all within the cloud environment. Once we're happy and once we're ready to start simulation, we can come along to this little button here, create a new simulation. As I mentioned, we're using Conjugate Heat Transfer V2 and create that simulation. And you'll see that a new simulation appears on the left-hand side. Now, we try and make this as simple as possible for you. So you start at the top, you work your way down to the bottom. When you get to the bottom, we'll be able to check the setup and start simulation. It should be feeding you the steps and the processes as you go through it. So the first thing that we do here is we might define a fluid. That fluid might be water or any other coolant. We can define that to be part of the fluid domain, volume, region. And we can also define the solid. Now, in this case, I'm just going to define the solid to be aluminium. Boundary conditions. We're not doing much here that's complicated. I'm going to say a velocity inlet, that it has a flow rate and we're applying that to the inlet boundary. Very simple. We're going to fix that at 18 degrees Celsius and save it. Where does the fluid come out? So in CFD, we'd like to tell the solver not only where the fluid's going in, but where it's coming out. And that's the basics of boundary conditions for CFD. So we're going to have a pressure outlet and we're going to assign it to that face here. So now we've got flow coming in at some flow rate and flow coming out at some pressure. And finally, we want to define the heat source for the battery. So for that, we define this top face. I'm going to assign it as a heat flux. And we can actually define the relevant power source for our particular problem in this field here. Once you're happy with that, press save. Now, I've done something wrong here, and I've done it deliberately, because when we come to checking our simulation setup, we don't want to start a simulation for it to fail later because of something that we could have caught at this stage. So we do that check for you. Press the stop, press run simulations. Anything in orange is going to be a warning. Anything in red is going to be something that we really do need to address before we start simulation. And in this case, we can see that there's something that we probably should do, and that is define the gravity direction. Now, in this case, actually, it doesn't matter too much, but we're going to do it anyway because that really is our iterative process. We've set up simulation, we've checked it, we've been given a recommendation, we sort the recommendation, we start the simulation. And once we're done here, then instead of getting any errors or warnings, we're actually going to get an estimation. This is done based upon machine learning algorithms, all of the simulations that came before it, and it tells us that this is going to take somewhere just over the hour. It's going to consume some resources. If you're happy with that, then you can hit start. And that's pretty much the simulation process from beginning to end. After this, you would get an email to say that your simulation is complete. Come back, have a look at the results. How do they feel? What can you get out of it? What design decisions can you make? And iterate. And that's the beautiful process of SimScale here. Now, of course, you could also have done parametric studies. We do have parametric capabilities. We could have done different temperatures, different flow rates, different geometries. That is, of course, all possible as well. Thank you for watching this demonstration. Hopefully you found it enjoyable and informative. And if you've got any questions, feel free to drop me an email. Thank you very much.